Now, to analyze how this solution behaves overall, I would like for you to notice something. I'm constructing this packet over wave vectors k1 that are all extremely close to the value of k0. In fact, that's precisely what I mean when I say I'm going to send in a beam of particles, right, an incoming packet of a particular energy. If it has a particular energy, then it should have a particular momentum associated with it. Now, it can't have a absolutely single momentum associated with it because that would violate Heisenberg uncertainty. So instead what we do is we make this Gaussian peak of momenta, right? But the picture that we have in mind is we're going to select these k1 with a very sharp Gaussian function so that they all are essentially have almost exactly the value, single value k0 representing the incoming targeted momentum. Consequently, it really is only one of these solutions of the time-independent Schrödinger equation which is relevant to the behavior of how this packet will interact with my system. So I want to see if we can save ourselves a little time in our general analysis by focusing really on the behavior of these time-independent parts. Now, there is a physical quantity that actually helps us to do that sort of a thing. And that quantity is the current density. You might recall that we had this probability current density. So we want to consider, right, the effects that come from a single value of k, in particular what we can expect because we're concentrating things around k0. And for a single value of k like that, then we know that our wave function psi of x and t would actually be a product, right, of the time-independent Schrödinger equation solution at that particular value of k0. Oh, and that does not depend on position and time. It actually depends just on position, but it has this very simple time dependence, which would then be a simple complex exponential that involves only a single value of energy because we're talking about a single value of the momentum divided by h bar times time t. Now, what I'm saying is that if I want to focus on the time-independent solution, I need somehow to get some sense of particle flow or motion or time in there. And the vehicle for doing that is going to be the current density, because actually I can calculate the current density knowing only the solution to the time-independent Schrödinger equation. So I'd like to take a look at how that comes about. So I want you to recall that the probability current density, J, which gives me the flow of particles in the rightward direction per unit time, at any location, is this factor we had h bar over twice the mass times I, and then there was a difference of two terms. There was my wave function, which of course was a function of x and t, times the x derivative of my wave function, which again depended upon x and t. And then there was a second term where I subtract off the complex conjugate of this. So when these are not both psi stars, I'm sorry. Where I subtract off the x derivative then of psi star of x and t, where that derivative then multiplies my wave function back again, psi of x and t. Now, the really neat thing with this very general expression is what happens when I substitute in a pure state, right? As I focus more and more near one particular momentum, I more and more just have one particular energy and phase factor. And let's see what happens if I actually have something that has just one term like this in my current density. So I'll have h bar on 2mi. The first thing I have to do is to calculate the complex conjugate of my wave function. That's easy enough. I would get the star distributes on both of them. So I'd have 5 star of k0. And this depends on just position x. Then the complex conjugate of the time-dependent factor would just give me the positive sign on I. There's e over h bar times t. Then I multiply that by the x derivative of the wave function itself, which again is a product of these two terms, phi of k naught, which depends on x. And now I'm just copying down the wave function, which has no complex conjugation, so it's the minus sign. So it's minus I e t in the numerator divided by h bar. That's the first term. Then I have the second term, which will be minus the x derivative of the complex conjugate of my wave function. And I've already written down that complex conjugate here. So that's simple enough to write down. That again is phi of k naught star, which depends only on x, times my positive exponential, which is e to the I, there's et over h bar. And that then multiplies finally my wave function, which had this phi of k naught, which depended upon position, times e to the minus I et again over h bar. And that finishes my second term. And that second term then, I'm not sure why I wrote this extra bracket here, right? That second term then completes my expression. Now, the reason why I'm going through this, the very beautiful thing that happens is notice these derivatives are with respect to x. The time-dependent factors are simply constants with respect to those derivatives, and they can be then factored out. And when they factor out, the beautiful thing is that they multiply together to give me just 1. They cancel out. So this cancels with this term, likewise in the second set of terms. So what you will notice is that the formula now for my current density is exactly the same formula I had before, but now there is only reference to the time-independent solution. So it would simply be phi of this particular k naught that I'm looking at, star, times the x derivative of phi, d by dx of phi, which depends on just this k naught, minus the x derivative of the complex conjugate, multiplied then by the wave function back again. So the expression, the general expression, works just as well if I put a time-dependent state or the time-independent solution. In this special case, of course, that I have just one type of energy oscillation involved. Now, that's very useful. So I can really just look at my time-independent solutions to determine my currents. The next thing I'd like to do is to consider then if I can go a little further with this current, because think about what this current represents. It represents the flow of probability per unit time. And what I'm interested in, one of the things that very much interests me, actually, is the ratio, right, of how many particles I send in this incoming beam to the number of particles that I get reflected back at me. Because the ratio of that tells me then the probability of the reflection. So it seems I have a way to get at that by just looking at the time-independent solutions. So let's go ahead then and consider calculating actually the probability of current associated with the pieces of the wave function from this first term. Now this first term is actually multiplied by all of these other constants. But I'm certainly getting tired of writing all of those other constants, so I'm just going to collect them together into one factor, which I'm going to define as n. N just stands for the normalization factor. So my time-independent wave function for the incoming beam, then, is just this n, this normalization factor, times e to the I k1x. So for the incoming beam, right, so if I want to understand the incoming beam, the corresponding wave that I want to analyze is just that normalization factor times e to the I k1x. And my job now is to calculate the current density associated with a term like that. So let's see. The incoming current then would take on the following value. There'll be h bar on 2mi times then, once again, I have to take the complex conjugate of my wave function. That's n star. And then, of course, I have to flip the sign on the I, k1x. That then multiplies the x derivative of this wave function. So d by dx of n times e to the I k1x. And from that, I then subtract the x derivative of my, I'll put the parentheses slightly differently, but it's the x derivative acting on the complex conjugate of my wave function. No problem. That's what I had just written here. That's n star with a minus exponential e to the I k1x. And that then just multiplies my wave function, which again is my normalization factor, times my incoming wave, e to the I k1x, like so. Now, when we look at this, we do have to take the derivatives. The derivatives are going to be fairly easy, though, because I have a constant, right, and I have an exponential. So all that these derivatives do is they pull down the factor that appears in the exponent. Otherwise, all of the other factors remain in place. So I'm once again going to have a situation where I have products of terms with positive and negative exponentials, which are going to cancel. So this first term then is going to give me something very simple when I evaluate it. The complex exponentials are going to cancel. N is a constant, comes out of my derivative. I will have something like n star n. And the only remaining piece after the exponentials cancel is the fact that the x derivative pulls down a factor of I k1. The second part then is subtracted off. It will follow exactly the same logic where I will get an n star n as my constant factors. Once I take the derivative and pull the factor out of the exponentials have opposite signs and will multiply together to give me 1. And all I'm left with then is the factor that comes down when I take the derivative, and that will have a factor then of minus I k1. And it's good that this came down with a minus sign because I have an overall minus sign out in front so that those minus signs cancel, and that these two terms then will add together rather than canceling out. Now, let's see what we really have here. There's some nice cancellations, I hope you will notice. There's an I in my denominator on the outside, and I have I's in these factors. So that I will kill this I and this I. Also, I hope you notice that I've got a factor of 1/2 out here, but I have just twice this first term. So I know I can get rid of the half and keep just the first term. And all that is left then is h bar times k1 times n star n. And don't forget, I also have my mass in the denominator. And I can rewrite this in a slightly more suggestive and convenient form. I want you to notice that this is just n squared, which is the probability density, actually. I want you to notice that. I just have modulo of n squared times some other factors, but modulo of n squared is just the modulo of psi squared. That's the same thing as modulo of the wave function squared, which equals the probability density in my wave. So that's interesting. That's the first factor I get. The second factor, h bar k1 over m, also has a very nice interpretation because h bar k1, that is just my momentum, and momentum divided by mass gives me my velocity. So this result that I have, which is the formal formula for the incoming current, that's my incoming current, I could have gotten much more quickly by simply taking the product of the probability density times the velocity of the incoming particle. So this actually gives me a very nice quick mnemonic for calculating current densities. You might remember actually that we had a very similar formula, or you would have had in electricity and magnetism theory, where you learn that the current density in that theory is the charge density times the velocity. So to get current of charge, I take density of charge times its velocity. And what I'm learning from my probability current is to get probability current, I take probability density and multiply that by velocity. So that's a nice way you can try to remember this particular formula. So we've got our particular result for the incoming current. And we also have this nice mnemonic to help us remember things. Great. So that formula I'm very happy with because what it tells me is the incoming probability per unit time in that incoming wave, which, if you want to think about it mentally, right, unit probability would be 1 particle per unit time. So incoming probability per unit time is going to be directly proportional to, then, the strength of my incoming beam. This is proportional to the number of incoming particles per unit time, and that equals this incoming current, and I have this nice formula for my specific case, n squared h bar k1 over m. Beautiful. Now, that's the incoming current density. Our job now is to look at the current densities in the reflected and transmitted pieces, and we can use this then to actually calculate things like the probability of reflection and the probability of transmission. So let's begin then by looking at the reflection. So for the reflection, the time-independent solution to the Schrödinger equation, this phi k of x, now is a little bit different. Instead of having a factor of 1 times n and a positive exponential, the main difference is now I have n times r as my factor, and that factor is actually multiplying a negative exponential. So from that, I can pretty much immediately, this is n times the reflection coefficient times a minus exponential. So from that, I can pretty much immediately write down what the current density in the reflected beam would have to be. There are 2 ways really to think about it. I could go back to my mnemonic that it should be probability density times velocity. My probability density is the modulo squared of my wave function, so that would give me modulo n times r squared. And then I should multiply by my velocity, which is the same velocity I had before, but of course these particles are moving in the backward direction. I would get minus h bar k1 over m as a factor. The other way to see this is, well, just to look at the mathematics. If I just replace n with n times r and k with minus k in my final result from before, I would get this result. It would be the same thing. Terrific. So now I'm enabled to actually calculate the probability for reflection. So the probability for reflection should be the fraction of particles that come back. So it's the incoming number of particles per unit time. It's actually the reflected number of particles per unit time. That's reflected divided by the incoming particles per unit time. Now this will equal the absolute value of the reflected current. And I want you to notice something about my reflected current, and then divided by the absolute value of the incoming current. Notice that this reflected current is carrying a minus sign. If I actually expand this out, right, I would end up with something like minus magnitude of n squared times magnitude of r squared times h bar k1 over m. All that this minus sign is telling me is that this is a backward flowing current. There's a backward flow, right? I know that it's traveling back at me to the left. That's why I'm calling this the reflected beam. That sign, though, is just telling me the direction of flow. If I want to know the total magnitude of the flow, the total number of particles per unit time reflected, I should look at the absolute value of this current. And likewise, the direction of the incoming piece isn't particularly interesting to me. It turns out to be positive, but nonetheless, I'm just counting particles to get my reflected probability. So I would use the absolute values, and then substituting in those absolute values, right, what I find here is n squared r squared on top times the velocity, and on the bottom I have n squared times actually the same velocity, because the magnitude of the velocity is the same for both the reflected and transmitted pieces. They both have this same k1, and then you'll notice there's a lot of cancellation. The n squareds cancel, these velocity terms cancel. And so the final conclusion that works in general is that if I ever want to know the probability of reflection, I can simply read off that reflection amplitude from my solution and then simply square it. So all of this information that's contained in the full time-dependent solution gets really all boiled down into just this reflection amplitude as far as telling me how much of a wave I get back. Now, we can test this also, right? We've actually done a different type of calculation. You might feel that this probability current idea is a little different. It's not as direct, but in our specific case, you might recall, we calculated the probability of reflection in an entirely different way. In this case, we had literally taken the area under the reflected packet and integrated under it, and we'd gotten an independent result. The result that we found for that case, though, I hope you will notice, right, is the square of this difference over this sum. But this difference over the sum is literally, when you look at it, that is the reflection coefficient, right? Which is multiplying the backward wave for my particular example. So in the case of this particular example, the reflection probability we would get from the formula that we just derived from current densities would indeed be this result, which is exactly the same as what we had calculated using the more direct area under the peak of the probability distribution. So that should help build up some confidence that this actually works and checks out. So this checks out in the step-down case. Now, if you're still not convinced, what you can do is you can go back and look at how we actually carried out the proof of that for the step-down case and the manipulations we made. And you will see that they, in fact, apply just as well to this more generic case without all the details being spilled out. You can carry out the same analysis to make a final formal proof that these two methods agree. Where this new current density method actually really comes into its own is when we look at the transmitted packet. The transmitted packet is a little bit more subtle. So let's look at the transmission. So for the transmission, in my general case again, my time-independent solution now has a somewhat different form. It has now, instead of the extra factor of r, it has an extra factor of t, the transmission amplitude, which is multiplying the incoming normalization. But then its exponential has a different wave vector. It has a wave vector k2. So let's think about the consequences of that. So now I have, instead of nr with a minus k1, I have an n times t with a plus I k2x. So we can run through the same logic very quickly. I hope we can pick off the current density now very easily. It's exactly the same type of logic. I should take the probability density of this, which would be its amplitude nt magnitude squared. I then multiply by the particle velocity, or in this case, h bar k2 over m is literally what will come out when I calculate my current density. Following again either a train of logic. So this gives me n squared t squared h bar k2 on m. And now I'm prepared to calculate the probability of transmission. And here's where things get a little bit more interesting. Once again, it would be the magnitude of the current that's transmitted versus the incoming current to give me the fraction of particles transmitted. I now have my n squared factor, my t squared factor, but what's different is that in the numerator I have a k2, whereas in the denominator, for the magnitude of the incoming current, I have n squared, and what enters there is h bar times k1 divided by the mass. There's, of course, much cancellation. The n squareds cancel. These constants, the h bar and the m's cancel. So what I'm left with now isn't exactly the quantum amplitude squared, which you might think would be what gives you the probability, but it also has a factor of k2 on k1. So I have k2 over k1 then times the magnitude of that transmission amplitude squared, and that then is the general formula. It's worth putting a box around it for the transmission you could find in any scattering problem. Before we leave these probabilities, I'd like to do one final cross-check that we've calculated this thing properly. And then we will move to a new topic. So, if I want to cross-check this, I can cross-check it with my example. And this is very useful with the step-down example. It's very useful because, we have this mysterious new factor, k2 over k1. It would be nice to see that it actually plays the role that it needs to. So the cross-check is, of course, if I take the reflection probability and add to it the transmission probability, I'm really thinking and hoping I had better get 1. So let's calculate now what we would expect here. So in the past, we actually had a result, and we've cross-checked it for the reflection probability. That was just the square of the difference in momenta over their sum, right? But now we have an entirely new formula. We actually never derived the transmission probability for the step-down case, but now we have our general formula that we can use. It's going to be k2 over k1 times then the square of whatever my transmission amplitude was. Now, we haven't extracted that, but we can pick it off very quickly from the solution. When we go up to the solution here, right, the transmission amplitude is whatever multiplies the outgoing wave. And what multiplies it is twice the first momentum over the sum. So in here, I'm then going to have twice k1 over the sum of k1 and k2. So now this is kind of fun, right? I've got this big garble of algebra. And I know, before I even try to simplify it from the physics, that this thing really better give me 1. And now we just have to play some algebra games to see if we can massage it to see if we actually get the 1. So let's try that. So to simplify this, hoping to get 1, of course I would put everything on their common denominator, k1 plus k2, quantity squared. Now the first term gives me the difference squared. I know how to handle that. That's k1 squared minus twice the product, k1, k2, plus the square of the second term, k2 squared. In addition to this, then, I have my new factor, and it has this mysterious k2 over k1 that must be playing some kind of an important role, and that multiplies then the square of the term in the parentheses, which would be 4 times k1 squared. Now, we may or may not be able to see quite yet that this is exactly 1, but notice something. This really emphasizes the importance of this extra term. If this extra term weren't here, this would become much more complicated to simplify. But because it's here, notice something interesting. It modifies the k2 squared, this k1 squared term, to become just k1. So what I have over here is 4k1, k2. But I have behind it, I've got minus twice k1, k2. So when I combine this term, after it's been modified by that ratio, with the first term, it becomes a plus 2k1, k2. So that becomes plus. That takes care of this term. And now we can notice, we can identify the numerator as, of course, just the square of the sum. And the denominator is also the square of the sum. And so then, of course, therefore, we indeed do get 1. So this really is the correct expression for the transmission amplitude, at least for this particular case. We've given now a nice proof of our new formula using current densities. And if you really want to triple check it, and you can find this in the class notes, you can do the formal derivations and manipulations to actually integrate up the area under the transmitted packet, following very similar logic to what we had done for the reflected packet in the step-down case. And that then tells us all about the reflection and transmission probabilities.